This is lecture 12. In this lecture, we'll be talking about chemical names and formula. So in this lecture, we won't actually be discussing a lot of chemistry per se. We'll really be building our vocabulary so that we can talk about chemistry, talk about chemicals. So by the end of this lecture, you should be able to name and identify all of these compounds or these different kinds of compounds. So we'll be discussing three types of ionic compounds. We'll be talking about metal cations complex with nonmetal anions. We'll be talking about polyatomic ions and hydrated salts. We'll also be talking about acids, specifically binary acids that consist of just two atoms, and oxoacids, which are nonmetal elements combined with oxygen to form acids. And finally, we'll finish off with covalent compounds that are consisting of just two individual elements. So by the end of this lecture, or the goal of this lecture and your goal in this unit is to be able to name all of these and derive their chemical formula from the name. So we'll start with metal cations. We've talked a lot about these, and some of these names won't be super surprising to you. But for main group cations, so these are your alkali metals, your alkali earth metals, and the first column in the P block. All of these, when they are metals and they are ions, we just refer to them by their element name plus the word ion. So here we have sodium plus, this is the sodium ion. Magnesium is magnesium 2 plus in its ionized form. And why is that? Well, it's because it's in the second column, so it's got to lose 2 electrons to become ionized. And that's by far the most common form of it. Aluminum is almost always aluminum 3 plus. So in this case, we just can throw the word ion in there, and we just assume you know how many charges it has. So if it's the ion in the first column, it's going to have a 1 plus. If it's the ion from the second column, it's going to have a 2 plus. If it's an ion from the first column in the P block, we're going to call it a 3 plus. So that's our main group elements. Transition metals are a little different because they can have more than one charge state. And so what we'll do is we'll have to indicate the charge in the name. So for example here, iron has 2 very common charge states. So it can either be a 2 plus or a 3 plus ion. And so we'd write iron parentheses Roman numeral 2 ion, or iron parentheses Roman numeral 3 ion. If you don't know Roman numerals, that's okay. We're really only dealing with the 1 plus, 2 plus, 3 plus, and 4 plus charge states in most cases. So Roman numerals for 1 is a single I, Roman numerals for 2 is 2 I's, Roman numeral for 3 is just 3 I's, and those are capital I's, by the way. And Roman numerals for 4 is IV. So for example, chromium 4 plus, we would write that as the chromium 4 ion. So for some ions, like zinc, which always forms the 2 plus ion, it may or may not be written which charge state. So some transition metals have multiple charge states, some only have a single one. For ions that, or for elements that only have a single typical charge state, sometimes we'll write in the Roman numerals, sometimes we won't. Okay, so this is our main group cations. These are things showing up on the left of the periodic table. Now let's go to the right on the periodic table and talk about our anions. So anions that are only made of one atom are almost always our nonmetal species. So that's carbon, nitrogen, oxygen, fluorine, sulfur, chlorine, bromine, iodine. So with these, when we're naming them, the ion, we're just going to add the suffix "ide" to the base name. So for example, carbon, when it's an ion, we'd call it carbide. Nitrogen would be nitride. Oxygen would be oxide. Fluorine would be fluoride. We have chloride, bromide, iodide, sulfide. So in this case, again, we're not indicating the charge on the ion in the name, and that's because we just assume the charge on these ions. So our halogens almost always have a -1 charge. Our halogens will almost always have a -1 charge. The oxygen and sulfur ions will always have a 2- charge. The nitrogen ion will almost always have a 3- charge. And when you get carbon with a negative charge on it, you're usually stripping everything off to a 4- state. Now this, and these actually increase in rarity as we go from right to left. So these halogen ions, super common. These group 16 ions are somewhat common. Nitride is getting pretty rare, and the carbide is extremely rare. All right, so those are anions. Now let's talk about the name that you get when you combine a cation and an anion. So this would be in the form of a salt. So in this case, all you're going to do, so let's say you have the sodium ion reacting with chloride. When those come together to form sodium chloride, you'll notice we just dropped the word ion from the positive charge and then just say the anion's name as well. So this would be sodium chloride. Now you'll notice that some of these, like potassium oxide, it has 2 potassiums and 1 oxygen in it. So we would write that name as potassium oxide, but looking at that name, how would you figure out that there are supposed to be 2 potassiums in here? Well, to do that, you're going to have to just know how many charges are on potassium and oxygen. So we know oxygen has 2- and potassium has 1+. And so if potassium only has 1+, we need to balance the charge in there, and so you're going to have to add 2 potassiums for every single oxygen. So here we're just going to have to know the charges and know how to balance that. Now the easiest way to figure out how to balance these, so for this one down here, for example, we have iron-3 oxide. Notice that we keep the charge of iron in the name because we still have to know the charge on it. It's not obvious. Like for aluminum chloride, we know aluminum is going to have a 3+, chlorine is going to have a 1-. But you'll notice in iron-3 oxide, we have 2 irons, 3 oxygens. How would we figure out those numbers to put there? The easiest way is if we look at the ions here, we have iron-3+. Since we have a 3+ charge on iron, that means we're going to have 3 of the other element. So iron is a 3+, we're going to need 3 oxygens. Oxygen is a 2-, which means we're going to have 2 of the other element. We're going to have 2 irons. So when we write this out in here, you'll notice iron-2 is complexing with O2-, or it's complexing with 3 O2-, and we're getting 2 iron-3+. Now, if you think through that, if we do 2 times 3, that's 6+, and 3 times 2-, that's 6-. So we have 6+ balancing with 6-. So it all works out there. We'll talk about that again in just a sec on this same slide. So for practice, how would we name these ions? You can actually stop the video here and try this out. Okay, we have sodium here, and we have bromine. So bromine is going to have a -1 charge, so it's going to be bromide. And sodium is going to have a 1+ charge, so it's going to be the sodium ion. So we're going to combine those to get sodium bromide. This next one is actually a little tricky, and you might have gotten it wrong, which is okay. The thing you might have gotten wrong was you might have forgotten to put the 3 in there on the charge on chromium. So this would be chromium chloride, because those are our 2 elements. Now, how would you figure out the 3 though in there? How would you figure out the charge on chromium? Well, chromium is a transition metal, and it can actually have multiple charge states. So you're not going to be memorizing the charge on chromium. What you're going to be doing is memorizing the charge on the halogens. Chlorine is a halogen, so it's going to have a -1 charge. And there's 3 chlorines here, so that means we're going to have a total of 3- charge. To balance that, we're going to have 3+ charge on the chromium. So that will be how you get your chromium-3 chloride. Let's try going backwards now and figure out what's the chemical formula of zinc nitride and copper-1 oxide. So you can pause the video again here and try and practice this. All right, so in this, we're going the other way, right? We're going from the name to the formula. And the tricky part here is balancing charge. I'm making special emphasis on this because it's a lot harder balancing charge when you're going from the name to the formula. So you have to know the charge on at least one of these species from memory so that you can figure out the charge on the other so that we can balance these out. And so we'll have to include enough of each ion to balance the charge. Right? Zinc is always going to be a 2+ charge state. It is a transition metal, but it's only got that one charge state, and you'll notice in here I left it off. And so you'll need to remember that zinc specifically has a 2+ charge state. You'll also need to know that nitride has a 3- charge state. So if nitride has a 3-, that means we're going to have 3 zincs. Zinc has a 2+, that means we're going to have 3 nitrides. So the formula here will be zinc 3 N2. So zinc 3 nitrogen 2. For copper 1 oxide, we're going to know that copper now has a 1+ charge state because I've indicated it in parentheses. And the oxide, you're going to have to know, has a 2- charge state. So if that has 2-, we're going to need 2 coppers. Since copper has a 1+, we're only going to need 1 oxygen. So the formula would be Cu2O1 or Cu2O. Let's try this again. What is the name of the ionic compound formed when bromine reacts with calcium? Go ahead and pause the video here and try and figure this out. All right, bromine is going to be a negative ion. Calcium is going to be a positive ion. These are both main group elements, so we're not going to need to indicate the charge in the name. So we're just going to have the calcium ion complexing with bromide, not bromine. So the answer would be calcium bromide. And then we could take that a little farther and ask, what's the formula for this compound with calcium and bromide? Well, now you do need to figure out the charge on each of these. Bromide's a halogen, so it's going to have a -1 charge. Calcium's an alkali earth metal. It's in the second column, so it's going to have a 2+ charge, which means since bromide's a 1-, we're going to need 1 calcium. Since calcium's a 2+, we're going to need 2 bromides. So we'll get CaBr2 as our formula here. So you can see you're going to need to be able to go back and forth on this. So let's try another one. Tell me what is the correct formula for magnesium phosphide. So I've already named this as this salt compound. Go ahead and pause the video and try and figure this out. Okay, what we're going to need to know is the charge on the magnesium and the phosphide. So the charge on magnesium is 2+ because, again, it's an alkali earth metal. It's always going to be 2+. For phosphide, how do we figure out the charge on that? Well, you can have that table memorized, or you can remember that it's 3 electrons away from having a noble gas configuration. So it's going to take 3 electrons, so it's going to be phosphorus 3-. Now, as for balancing out, now we have phosphine with a 3- charge, so we're going to need 3 magnesiums. Magnesium has a 2+ charge, which means we're going to need 2 phosphates. We're going to get Mg3P2. So our answer there would be C. All right, so that is our monoatomic ions, or monatomic ions, ions that only consist of a single ion, how we make those, or how we name those and how we name the salts. Now let's get into polyatomic ions. So these are ions basically of molecules. So in these ions, you have covalent bonds, but you also have a net charge, whether it's positive or negative. So for example, in nitrate here, you have nitrogen in the middle, covalently bound to 3 oxygens. And so this would be NO3-, also known as nitrate. In hydronium, you have an oxygen covalently bound to 3 hydrogens. And in NO2, you have nitrogen covalently bound to 2 oxygens. Now, how do we know the names of all of these? So there is actually some method to the madness in naming these, but it's pretty complex. And so the real answer is you're going to have to memorize the names and formulas of all of these. And when I say all of these, it is a big task, but it's pretty doable actually, once you try and memorize these names for a while. These are all of the ions you'll need to memorize. This is also found in table 4.4 of your book. In table 4.4, you'll notice the ions are in slightly different order. That's totally fine. It's still the same list of ions. But you're going to need to know the name, the formula, and the charge on each of these ions. Now, fortunately, the charge on most of them is 1 minus. So we've only got a couple of exceptions. So ammonium here, the ammonium ion has a positive charge. We've got a couple like chromate, dichromate, and disulfide here that have multiple charges on them. The phosphate and sulfites all have multiple charges as well. But you're going to need to go back through that and memorize this table. So for the rest of this lecture, I will give you examples as if you have this table memorized. And so if you don't necessarily, or if you're not necessarily able to name all of the compounds when we're talking about these polyatomic ions, at least during this lecture, that's fine. But you do need to memorize that for the future. And then, of course, we have these polyatomic ions forming salts too. So here we have the ammonium ion and the phosphate ion. And when these two complex, we will get ammonium phosphate, right? So the naming rules are actually the same as for our monoatomic species. We're still just going to take the name of one ion and the name of the other, put them together, and you'll have to know how many charges there are. If the charge is ambiguous, we're still going to put the charge in parentheses. Now, let's talk about, though, the parentheses in these chemical formula. So, for example, we have NH4 here in parentheses with a 3 after it. Why are we doing that? Well, this parentheses means that there are 3 of everything in the parentheses. So there's 3 NH4 groups complexing with this phosphate. So why don't we just write, instead of using parentheses, why don't we just write N3H12? Well, the answer to that is we're specifically trying to indicate that this is the ammonium ion complexing with the phosphate ion. So if we did N3H12, now that's ambiguous and we lose information. And so we like to keep that in parentheses. Now, when do you actually need to use parentheses? It's when you have a polyatomic group, in this case, a polyatomic ion, that you want to indicate there's more than one of. So for example, here I have PO4. This 4 isn't indicating that there's 4 POs. We have 1 phosphate, and phosphate consists of 1 phosphorus and 4 oxygens. You'll notice here too with iron, we didn't put iron in parentheses because there's only a single element there, only a single species. So we're saying there are 2 iron ions, but since it's monoatomic, there's only 1 element there. We don't need to put that in parentheses. But iron here is complexed with the sulfate ion, SO4, and there are 3 sulfates because this is iron 3+, so we're going to need 3 sulfates to balance out the charge, and we need 2 irons because sulfate has a 2- charge. So that's when you would put parentheses into a chemical formula. And again, notice that those parentheses are not showing up in the actual names of these compounds and salts. The only thing that would be in parentheses here is the charge. Okay, let's have some practice here. So let's figure out how I would go from the name here of this CR parentheses ClO43. Well, for this, we'd have to know what these species are. So we'd have to know what chromium is, and we'd also have to know what the ClO4 species is called. And this is called perchlorate. And so we can get chromium perchlorate if we've memorized the name of that perchlorate ion. But then there's also the issue of figuring out how much charge is on the chromium. Now there's 2 ways. One way is you can remember that perchlorate has a 1- charge, and you do actually need to remember that perchlorate has a 1- charge. But another way is you'll notice there's 3 perchlorates, which means there's going to have to be 3 charges on chromium. So since there's 3 here, we can just say chromium 3. So you can see from that example, you actually don't need to know the charge on this species to know the charge on chromium in this example. We just know that chromium is complex to 3 things, and that means it's going to have 3 charges. How about this one, NH4NO3? So for this one, again, you'd have to know the names of these species and which specific groups are the ions. We'll know where to cut that boundary off. So that just takes memorization. So the first is this NH4 group, that's the ammonium ion, and the second is the NO3 group, that's nitrate. You'll notice neither of these are in parentheses. There's no subscript, which means that there's just one ammonium and one nitrate, which means that each of these is going to have a 1+ charge. The name of this then is ammonium nitrate. And again, to get that answer, you'd need to memorize those formula, and you do need to memorize them. Now let's write the chemical formula of these species based on the name. So here we have lithium bicarbonate, calcium hypochlorite. So for these, again, this is going to take memorization. And since we have a name, though, we do have to know something about the amount of charge on each of these. So lithium is an alkali metal. It's going to have a 1+. Bicarbonate is going to be a 1- ion. So these will mix at a 1-to-1 ratio. And the formula for bicarbonate is HCO3. So lithium bicarbonate is very close to the formula for baking soda. Baking soda is actually sodium bicarbonate. And so lithium bicarbonate and sodium bicarbonate actually have very similar chemical properties. All right, now we have calcium hypochlorite. So in this one, we're going to have to know what hypochlorite is. And we're going to have to know how much charge is on these species. So hypochlorite is a 1- ion. Calcium we know is a 2+ because it's an alkaline earth metal. And so we're going to have 2 hypochlorites to balance out that charge. So the formula here would be just Ca parentheses ClO close parentheses 2. And so now we have hypochlorite. You'll notice that has a chlorine and an oxygen. We also have perchlorate, which you'll notice has a ClO4. You'll just need to memorize the perchlorate and the hypochlorite and get those straight in your mind. So let's practice a little with this. And give me the chemical formula for the ionic compound that contains magnesium and hydroxide. Now, for this problem, you actually don't need to know the charge on hydroxide because there's only one answer that'll be correct based on the charge on magnesium. So go ahead and pause it here and try and figure this out. So what I meant by that clue I just gave is magnesium is an alkali earth metal. It's going to have a 2+ charge state, which means you're going to have 2 hydroxides. Now hydroxide is our OH group, and so we're going to just be able to pick the answer that has 2 hydroxides in it. There's only one of those, and it's C. Now I could give you a more complex question on an exam where I say, where I give multiple options where there's an OH with a 2 after it. And in that case, you'd have to know the charge on hydroxide to figure out how many magnesiums there are. So for example, I could give magnesium 2 OH2, or I could give magnesium OH2, and you'd have to figure out which of those is correct. But what is the name of this compound right here? Well, it's got the magnesium ion and it's got the hydroxide ion. Those will be combined to just give us magnesium hydroxide. Now, hopefully you're not feeling too overwhelmed by this. Really, with naming, it's memorizing a lot of rules. There are some principles to it, but if it feels just like a ton of memorization, that's largely because it is. And again, this isn't necessarily chemistry per se, but we do need this tool of language to talk about chemistry. All right, now let's talk about something else to do with salts, and that's hydrated salts. So far with salts, I've just given you the idea of a cation and an anion complex. And so that is what a salt is. But something else can happen to a salt, and that's hydration. So if I have a salt structure here, and the structure is outlined or is highlighted in the red, sometimes it can absorb or trap water. So in this salt structure, all the blue here would be the water, and it can get trapped inside our salt crystal. And when that happens, we say the salt is hydrated. So for example, copper sulfate, it can actually absorb 5 waters, and then we would call it copper 2 sulfate pentahydrate. Notice that the actual name of the salt doesn't change. So we still have copper sulfate. We're still having to indicate the charge here. And interestingly, I will give you this bit of information. You'll notice that copper here has a 2+ charge state, but we've only got one sulfate. Why is that? What's going on? Well, actually, sulfate has the same charge as copper. So in the rare case, when your anion and cation have the same charge, then you could write copper 2 sulfate 2, but then that number can be reduced just to copper sulfate. Okay, but we're focusing here on the water. Notice that I've indicated with a dot here that this is some hydrate coming in. It's not necessarily a part of the salt, but it's definitely present around the entire salt. So I give it that dot, and then I just say how many waters there, and then I write water. Now this pentahydrate here, penta means 5, and hydrate means water. And so you're going to change this prefix, penta, depending on how many waters are present. And so we'll have this list. And this is another thing you'll need to memorize. This one isn't super hard because you've heard a lot of these prefixes most of your life. So if you have only one or only half a water, which you might think, how do you have a half a water? Well, this would be a case where, let's say you have 2 sodium chlorides sharing 1 water in between them. The reason this works is because the water is not really a part of the salt, it's just there. And so if we're saying we have a hemihydrate, that means we have water and the salt there at a ratio of 1 to 2. So 1 water for every 2 salts. If you have 1 hydrate or 1 water, you'd say monohydrate, 2 would be dihydrate, 3 would be trihydrate, then we have tetra, penta, hexa, hepta, octa, nona, and deca. So for example, we could have iron 3 chloride. Iron 3 chloride picks up 6 waters, 6 is hexa, and so this would be iron 3 chloride hexahydrate. BaCl2 can absorb 2 waters, so that would be barium chloride dihydrate because of 2. And that's really all there is to naming these hydrates. You take the salt, you add the number, and then the word hydrate. So you add the number as a prefix to the word hydrate. And hydrated salts are important, so we actually see them in all sorts of applications, and they do change the chemical and physical properties of the salts when they absorb water. So here, what I have is what we call anhydrous cobalt 2 chloride. Anhydrous just means no water. And so we put anhydrous in front of salts that regularly absorb water to indicate specifically this is the water-free version. And so you'll see that name anhydrous quite a bit on chemical bottles. So anhydrous cobalt 2 chloride is this bluish purple color, but then when it absorbs its water, so it's hexahydrate, you'll notice it turns a reddish pink color. And so this absorption has real effects. Another common salt that absorbs moisture is calcium chloride. And this guy is really good at absorbing water from the air. It's used a lot in humidity and dust filters. Another place we see salts that get hydrated are in desiccants. So the idea in a desiccant is we're taking the anhydrous form, putting it in a package that has moisture, and then it will absorb the moisture to become the hydrated salt, and then we've eliminated the water from the air. So you see desiccants a lot, right, in pill bottles, sometimes, or a lot of times in beef jerky for some reason. I'm not entirely sure why. If you crack these open, these desiccant packages, you'll just find little crystals corresponding to different salts, whatever salt is in there. Another huge place that desiccants are found are actually in things like diapers. So diapers, you don't feel a salt in there, and that's because this is a salt made of a really long carbon chain. So it's actually a molecule salt where the molecule itself can be thousands of carbons long, and every couple of carbons you have a branch off where you have a CO2 minus group on there. So that's 1 carbon, 2 oxygens with a negative charge. So each of those CO2 minus groups can then hold a sodium plus on it. And so you actually have this carbon chain that can have hundreds or thousands of charges on a single molecule that's then balanced by this sodium salt. So you have this really complex salt. And the reason these kind of fabric salts are really nice is because they can actually absorb 200 to 300 times their own weight in water. So this is a low weight desiccant that can be carried around with you, right? We also see these showing up in things like panty liners, tampons, and breast pads. Anything where you'd need a low weight absorbing material, these are great for. All right, so that's it for hydrated salts and their applications. You'll notice hydrated salts really not a complex subject. If you struggle with them, though, let me know. Now we're going to shift focus to acids. We're going to touch on two types of acids, so binary acids and oxoacids. So a binary acid is a really simple acid. By binary, we just mean two, and we're talking not about two acids, but two atoms in an acid. So for an example, in hydrobromic acid, we have one hydrogen and one bromine. So this is called hydrobromic acid. So the way we name these, we put the word hydro at the front, we put the halogen base name, when we add ic to that halogen base name, and then we add the word acid. So since this is the acid made from bromine, it would be hydrobromic acid. And these are almost always halogen acids. So we have hydrofluoric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid. And these acids are actually extremely common, so we really want to focus on their naming. These acids are very strong generally and used in a lot of places. So actually HCl, HBr, and HI are all extremely strong acids. Hydrofluoric acid isn't as strong, but it's also very dangerous. Okay, so that's really all there is to naming binary acids. So you can either memorize this scheme for naming them, or you can really just memorize these four acid names: hydrofluoric, hydrochloric, hydrobromic, hydroiodic. And for me, memorization of these names just came naturally because we talk about them constantly. All right, now our oxoacids. Memorization of these names is not as straightforward just because there's a lot of them. These are all pretty important acids, but there's so many of them that keeping their names straight can be a little more tricky. So with an acid, you'll notice that all of these have hydrogen on them. And I'm going to jump back to the previous slide. You'll notice all of these acids have hydrogen on them. So what an acid is kind of like a salt, although in an acid you have a covalent bond to that hydrogen, but then it often breaks apart to give you two ions. You'll have your proton, your H+, so that's just a hydrogen atom minus an electron. And of course, all hydrogen is a proton and electron, so if you steal the electron, it's now a proton. But acids are just giving off this proton. And so I'm going to jump back now to our oxoacids. And in these oxoacids, you'll notice these all have oxygen, hence the name oxoacids. And these are all just the protonated forms of anionic salts, or anions. So for example, we have nitrite, which is going to be on your list of anions to memorize. And it's got a -1 charge on it. So we're just going to stick a single proton on there and get nitrous acid. Then for nitrate, so you'll notice the difference between nitrite and nitrate is nitrate has one more oxygen. And if you have an anion ending in an 8, its acid is going to end in ic. So this would be nitric acid. If you have an anion that ends in ite, then its acid is going to end in us, so nitrous acid. And you'll notice the pattern's the same. So sulfite goes to sulfurous. You notice you have to play with the sulfur name a little bit in there. But sulfate goes to sulfuric acid. Phosphite goes to phosphorus. Phosphate goes to phosphoric. And now let's talk though about how many protons are on each of these. So you'll notice sulfate, it has a 2- charge, so we're going to have to put 2 protons on here. Each of those hydrogens has a 1+ charge, and so we're just going to balance that out. Then we got this series, hypochlorite, chloride, chlorate, and perchlorate here. These all have a single charge on them, and so they're all going to just get a single proton. They're going to become hypochlorous acid and chlorous acid. You notice that we keep the hypo here, so it's going to be hypochlorous. And for the perchlorate, so we're ending in 8, so we're going to change to ic, but we keep the per on there, so it's going to be perchloric acid. And then acetate down here, notice this is a much more complex anion, and this is showing up all the time in chemistry. So if we put our extra proton on, you'll notice that this one is actually the only one that has a proton at the end. Usually a great way to determine an acid, or if a proton is acidic, it's going to be falling off real easy, is most of the time we'll write it at the beginning. However, anytime you see this, COOH or CO2H, you'll also know that's an acid. So we'll get into why we write this out as COOH in a little bit, but part of it is to indicate that this, or in a later lecture, but part of it is to indicate that this proton is attached to one of these oxygens. And so for this, we still go from acetate to acetic acid or acetic acid. And this is actually the acid found in vinegar. It's what gives vinegar its flavor, that really sour flavor and smell. Okay, so that's acids. Now let's go to binary molecular compounds. So these are compounds that consist of only 2 elements. So the way we're going to do this is first, and I'll make this point, this is between 2 nonmetals. It could be between a nonmetal and a metalloid, but this isn't going to involve metals. So whenever we have metals, we pretty much always have an ionic compound. But when we have 2 nonmetals, what we're going to do is we're going to give our first element name, and we're going to put a prefix on it indicating how many are there. So for example, if I have 2, I'll put di. If I have 3, I'll put tri. So if this is bromine, I'd put tribromine. And then for our second element in this, we'd also put the prefix, but here we'd put the base name and add the suffix "ide." So for example, here we have SO3. For S, that's sulfur. So we're going to ask how many are there? There's 1. So we'll look up the prefix there, that's mono. But you'll notice we don't actually put mono here. So this is a special case where you don't use mono on the first element. If there were 2 sulfurs here, we would put disulfur trioxide. But since there's only 1 sulfur, we're just going to say sulfur trioxide. And you'll notice that for oxygen here, we didn't put sulfur trioxygen. We changed that oxygen to an ide, so oxide, and we get sulfur trioxide. Now, if the second element is or does have only 1 atom present, we do add that mono to it. So CO, there is 1 carbon, but we're not going to write monocarbon. We're just going to put carbon monoxide. So we have that 1 on the second one. And you'll notice that here we just put monoxide, not monooxide. Sometimes when it's pronounced, you'll hear someone say monooxide, but generally carbon monoxide is what you hear, and that's the correct way of doing it. So if your element starts with a vowel, and your prefix ends with an O or an A, we'll drop that. You'll notice that in trioxide, we didn't drop the vowel from the prefix, but in mono or monoxide, we did. So when it's an O, so if there were 6 oxygens here, that would be hexa. So we would drop that A and it'd be hexoxide. And that's just a rule that makes it a little easier actually to pronounce these. And here's another example here where we have N2O4. So here we have 2 nitrogens. So you'll notice we're finally putting a prefix on the first element. So this would be dinitrogen. And here we have tetroxide. We don't have tetraoxide. We have tetroxide. So we've dropped that A from the tetra because oxide begins with a vowel. All right, let's finish up with some practice here. Practice naming these compounds. So we've gone through a lot of rules, but one thing that we haven't really pointed out is that when you look at a compound like this, KNO3, you're going to have to be able to identify first whether it's an ionic compound, an acid, or covalently bonded or molecular compound. And a lot of that is just going to come from memorization and practice. But in this species, KNO3, I want you to tell me whether this is A, an ionic compound, B, an acid, or C, a covalently bonded compound. And after you identify that, I can give you the name. So go ahead and try and figure that out. Pause the video. All right, so this is a metal complexed with some non-metal species. So right away, you can say that is an ionic compound. Anytime you have a metal with a non-metal species, you recognize that as ionic. And so here we have the potassium ion complex with a nitrate ion, so that'll be called potassium nitrate. Next, let's go with BF3. Is this ionic, an acid, or covalently bound compound? Go ahead and pause the video. All right, so there's no metals in here, so we know it's not ionic. There's no protons, so it can't be an acid. And so it's got to be C by default. It's a covalently bonded compound. And how do we name this? Well, there's one boron, and so we're going to leave the mono off that, so we're going to call it boron. There's 3 fluorines, so it'll be trifluoride. Next is N2O, which is laughing gas. No metals in here and no protons, so this is not going to be ionic or an acid, so it's going to be C, a molecular compound. And so this will be dinitrogen monoxide. Sorry, I didn't let you pause it on that one. So let's try this one. Go ahead and pause, try and figure this out. All right, there are no metals present here, so it's not an ionic compound. We do have this ClO4 group here, which is perchlorate. We also have the proton written at the very beginning of this formula. That's a good indication that this is an acid. So this is B, an acid. And since we have perchlorate, we're going to change that to perchloric acid. And let's go on to the next one. So this is bleach. So this is NaClO. Go ahead and pause. Tell me what kind of compound it is. Okay, so this has a metal, which is going to say it's an ionic compound. So it's A. And this is going to have sodium and hypochlorite in there. So the name will be sodium hypochlorite. All right, so that's bleach. Let's look now at baking soda. Give me now whether this is ionic, an acid, or covalently bound complex. And actually, let's try and figure out the formula. Now, if you don't have all the anions memorized, that's fine, but go ahead and pause it, at least try and figure out what kind of compound it is. Okay, so sodium is a metal, which means this is going to be A, an ionic compound. So then we have sodium bicarbonate. Bicarbonate is just HCO3. Now, you might notice that in bicarbonate by itself, we have HCO3, we have the H written at the beginning. So you might ask, well, is H3CO3 an acid? Actually, it is, but we're not going to worry about that right now. For right now, we're just going to think of bicarbonate as an anion. And later, when we get into acid-base properties, way down the line, we can figure out what bicarbonate is going to do with that proton. Now let's talk about sulfuric acid. Now you should be able to figure out from the name here that this is B, an acid, and its formula, since sulfuric acid is derived from sulfate, and sulfate has a 2- charge, then you'll know that sulfuric acid has 2 protons in it. The last one we'll finish up with here is a type of moss killer, iron 3 phosphate octahydrate. Okay, now here you'll notice we're including the hydrates. You should be able to get everything here except for maybe the phosphate. But go ahead and pause this and try and figure this out. All right, for this is going to have iron, so it's going to be an ionic compound. And phosphates formula is PO4, and we know that we're going to need 2 phosphates because iron has a charge of 2. Now to figure out how many irons you need, of course, you'll have to know the charge on phosphate. Phosphate has a charge of 3, so we'll need 3 irons. I mean, you should have been able to get this octahydrate here. Octa means 8, just like an octopus. All right, so now you should know how to write the formula for something like dinitrogen pentoxide. If I gave you that, you should be able to tell me that that's N2O5. But looking at N2O5, that doesn't actually tell me what the molecule looks like, doesn't tell me which atoms are connected to which. You know, we have 2 nitrogens, and you might guess that those 2 nitrogens are bonded to each other and bonded to some of the oxygens. You might have no clue to guess that. But we know that if there's 5 oxygens, there's going to have an unequal distribution maybe on the nitrogen. So maybe we have the 2 nitrogens with an oxygen in between, and then we have oxygen stuck on there. But how can we tell, how can we figure out what N2O5 is actually going to look like without just Googling the formula or Googling the structure of the compound? And so that's actually where we'll go next. We'll finally get into the part of chemistry you thought you were going to start with a month and a half ago, which is looking at molecules and figuring out what they look like.